Greetings, FRC Robotics Engineer Kevin O'Connor here with a video for you on LabVIEW debugging for FRC. So this will be a short video on some of the techniques that you can use to debug LabVIEW programs in FRC. So as you can see, I've opened up this year's version of LabVIEW and a couple of windows here. So I've got my driver station open already right here. I have my Project Explorer, from which I've double-clicked and opened the robot main front panel right here. I also opened the Teleop VI front panel, which I'm going to leave in the background for now. We'll talk about that in a little bit. And then used either the key combination Control-E or Window Show Block Diagram to show the block diagram here of Teleop. So the easiest way to debug FRC LabVIEW programs is to run them from the computer. Instead of doing the build and deploy that's down here in build specifications, right down here, we're going to run it dynamically from the computer. So that's why we have robot main opened up here. So we're going to click this little white run arrow, and the program's going to download. This is telling me that I already have a program running on the RoboRio, so I'm going to press OK to allow LabVIEW to close it. We're going to check this close on successful completion box so that this deployment box will go away and our program will begin executing as soon as it finishes downloading. So as you can see, it's taking a little while to copy over here. Generally, when you're downloading LabVIEW program after a LabVIEW program, it will run pretty quickly. You may sometimes get these save dialogues. We're just going to go ahead and click save on all of them that pop up. But as I was saying, your download times on subsequent small changes of the program should be pretty quick because it's not going to go ahead and re-download all of this. I either didn't have a LabVIEW program on here since last time I formatted this, or my last program on here was a C++ or Java program, or a very different LabVIEW program, or something like that. So this is going ahead and downloading, all the different WPI LibVIs that are used in here. But subsequent deploys of this program, which we probably will do one or two, you'll see that they'll go much, much quicker. While I'm waiting here, we're going to pull the driver station back to the top. Because to get this Teleop VI to run, what we're going to do is once the code loads, we're going to enable in teleoperated mode to get this VI that we're using for our demo here running, so we can take a look at some things, different tools that are available for debugging LabVIEW programs. Alright, so our code's now up and running. We can see that by the white arrow turning to this black arrow in robot main. Teleop is not yet running. We can see this little tiny black arrow inside white arrow shows that the program that this is contained in is running, but this VI is not. So we're going to go ahead and enable this. Now you can see it flashing each time Teleop gets called. So this is getting called every packet from the driver station to the robot. So the first tool that we're going to show for debugging here is called the probe tool. So if we hover over any wire, like one of these joystick axes here, we get this little P in a circle tool, and that's the probe tool, and we can left click, and the probe watch window pops up. So this is saying that the value of that joystick axis is 0, this one's 0. So I do have a joystick plugged in, but it is centered right now. So now we're looking at both the X and Y axis. And so as I move the joystick around, we can see it go to -1 on the Y, which is our bottom probe, +1. Top probe, we can go to -1 all the way to the left. And you can see the other one move a little bit as I'm not moving the joystick perfectly straight. But now if I go to like the corners, you can see these values change dynamically as I move the joystick around, hold it in different places. We can see what the values are. So this is one tool that you can use to see what values of things are as the program is running dynamically. So that's the first tool we have available, is the probe window and placing probes on the diagram. So the next thing I'm going to show you is the highlight execution. You should be very careful. The probe window, the code is still running at basically full speed. Depending on the specs of the computer, as you open up a number of front panels and probes and things like that, it can slow down execution a little bit. But in general, the code will continue executing as expected. With this next tool, the highlight execution, you should be more careful to make sure that mechanisms are not going to move past limits, or that the robot's not going to take off unexpectedly or things like that, because this will slow down the execution of the program, which may result in those types of behaviors. So we're going to go ahead and click this little light bulb up here, and as you can see now, it's stepping through with these little dots traveling down the wires, and it's showing us what values it's passing through. So right here, it's showing us what it passed through into the arcade drive VI. So there's this little button next to it, retain wire values. So this is a toggle on whether or not to continue showing the values on the wires after it moves on to the next step. So here we go into the arcade drive VI, and you see these values stay on the wire. If I hover over them, they sort of disappear. These wires are on top of each other a little bit, so it doesn't work great. But you can see that value stay there this time as the code continues executing until a new value writes over it. If we push this button again to not retain wire values, we see that they do not. Alright, so that's the highlight execution tool. That can be kind of useful when you're looking at things like case statements and trying to see which case is executing or the flow of a state machine. But as I said, be careful that mechanisms are not allowed to drive past their limits or other things. As you noticed, those dots were moving across pretty slow. It definitely slows down the execution when LabVIEW is trying to show you exactly what's happening by a very substantial amount. Right now, this is executing and returning almost immediately and getting called every 20 milliseconds. As you could see with highlight execution on, it was taking much more on the order closer to seconds as you saw those dots moving across the screen for each call of the teleop VI. So the last tool I'm going to show you is, we're going to go ahead and finish robot main. And we're going to talk about the front panel. So I'm going to stick something on the front panel for these joystick axes. So LabVIEW front panel is updated dynamically. This you can use this a lot like the probe window, but depending on how things are updating and how you want to visualize them and how many things you want to visualize, sometimes the front panel may be better than a probe. Other times it may not. Sort of personal preference. So we're going to go here in teleop. We're going to grab one of these joystick values, right click, and select create indicator. And so this is going to create an indicator on the front panel of this joystick value. So right now it's a number. That's going to give us about the same thing as the probe display, so that's not that useful. So we're going to go to right click on it, select replace, and we're going to find, so this is numeric indicators, and we'll make this one vertical slider. And then double clicking on the top value, because we know our top value is 1, double clicking on the bottom one, setting it to -1, because that's We know the range of our joystick is. So now we have a real quick fill slider for our joystick. So we go back to robot main, select run. Teleop has changes, we save them. As you can see, this deploys much quicker because all of these VIs are already deployed to the target. Now we're running again. We go back to our DS and enable. Alright, so now we have our slider on the axis of our joystick, and as I move the y-axis of the joystick, as I move it away from me, it goes to -1. As I move it towards me, it goes to +1. And we can see the same values being shown here in our probe window. So if these values were updating very quickly, because they're decimals, you see this E-3. If it was bouncing between, E-3, E-2, it may be very difficult to see in a probe window exactly what's going on. A slider or something like that may help a little more, especially if you've got values you're trying to compare to each other or something like that. Sometimes it's just easier to visualize these things as a slider, or a gyro value as a circular gauge or things like that. There are a couple different options that you can play around with. Most of the time you'll just use probes, but this is something that is available. Alright, so we finished debugging our LabVIEW program. Works the way we want. We go here under build specifications, right click, we do a build, and then we right click and run as startup after the build is complete. For any of you that are not familiar with the deploy process for LabVIEW programs, that's what you're going to do there. While that's running, I'm going to pull up the front panel again just to talk real quick about some pitfalls and things you may be looking for when you're debugging LabVIEW programs. So this is the basic program that comes out of the box with just joystick driving arcade drive. Some of the things you really want to be looking for are teams using additional copies of these robot drive VIs for other things like mechanisms. That should work in general. It may not be quite as flexible as using the raw motor VIs, but if they're trying to drive multiple things together, sometimes teams find that the easiest way to do it. I prefer Y cables on the motor controllers unless they're CAN controllers. But some teams prefer to use these. The thing to watch out for is that by default on the drive modules here, the motor safety is enabled, and it's not for raw speed controller or relay objects. And what that means is that you have to update the value of this drive object every 100 milliseconds. Otherwise, the code is going to determine that one of your loops or threads is hung, and it's going to disable that motor for you. So that's on by default for the robot drive and not for other items. The biggest area you run into that is in autonomous, where teams are doing these timed sequenced routines and they expect things to run through, and they put pauses or delays in there where they're not feeding the motor, and then the program stops the motor for them as the motor safety triggers. So the way around that is there is a delay and feed in here, this auto delay and update safety. So if you're using a robot drive in autonomous and you're trying to delay some certain amount of time, or if you're doing it in teleop for a mechanism and you're working on things by time, putting an arm up for time or down for time, and they happen to use robot drive. Actually, this VI is only suitable for autonomous because this will delay itself. So you feed in the delay time and the robot drive object, and this is going to go ahead and feed the robot drive as it's doing the delay. So this is the same thing as having this delay here. Nope, sorry, that was the tick count. Let me grab the delay. Same thing as having this delay. This delay, the object here takes seconds, this one takes milliseconds. That's the only difference. So if we want to delay for 1 second, again, you should not put these where I'm putting them here. They're just a blank space to throw throw these VIs down on. You really don't want to pause in in teleop like this, and that's something I'll walk through in just a second as the next pitfall. So this will delay for a second, this will delay for a second, but this top one will continue to feed the motor safety and keep your drivetrain running, you know, straight, turn, whatever it is you're trying to do. This bottom one, after 100 milliseconds, the motor safety will time out and it will stop. So that's something to watch out for with the robot drive object, where that safety is on by default. So as I mentioned, the next thing to watch out for is loops, delays, things like that in this teleop function. So if you see these guys floating around here in teleop, these are something you don't want. You want this is going to be called approximately nominally every 20 milliseconds. So it should take less time than that to execute. So it is possible to put very small delays in here if you have to. But generally there are other ways to solve those problems, and it's really not something you want to do. The other thing to look out for in here is things like this. Again, there are certainly right ways to do this if you're looping through an array or a set of values or something like that, and there's no delay guy in here. This may be okay as long as it ends reasonably. But generally things like that will be this for loop, not the while loop. The while loop is pretty dangerous in this teleop VI. If it gets stuck in here, you're only going to go through your code once, and you're not going to be able to continue updating based on new joystick values and things like that. So if these are in here, you want to make absolutely sure that there's some sort of timeout associated with this stop condition, or some way to know that you're definitely going to get out of this loop within 20 milliseconds. For loops are a little bit safer because you're doing it for a certain number, but again, you just want to make sure that there's bounds, some way of limiting this loop count. So if it's a fixed loop count, that's fine. If it's coming off of some variable, you want to make sure you're either very certain of the bounds of that variable, or that you coerce it with an in-range and coerce. We put the coerced value in here, and we set limits. So if we're not absolutely positive that we know the limits of this, we're going to say the lower limit is 0 times. The upper limit, we don't want to run this more than 10 times, whatever it is. And I'm going to, for now, stick a constant in here, 5. But this is where your variable could be if you're running some sort of iteration over a loop. So this, variable value feeding in the middle here, we know this shouldn't run more than 2 times, or 10 times, excuse me. This value shouldn't be more than 10, but we don't trust that it never will be. We're reading it out of a file or something, and we want to be absolutely certain, even if the file is corrupt and the value that gets read in is, 100,000, we don't loop through this 100,000 times. This will coerce it to be 10 times. So those are some of the big pitfalls to look out for in teleop, is those loops and delay statements. I'm going to hop into robot main here. Let's close this probe window. Yes, I wish to continue. Hop in robot main. This is what robot main looks like in the default framework. You want to make sure they haven't made any modifications to this unless they really know what they're doing. It's pretty easy to get yourself in hot water real quick making modifications here, other than if you're absolutely sure you're not using vision processing and you're not trying to pass through images from the USB camera. It is safe to get rid of that, no problem. If you ever want it back though, you have to make sure you get it connected correctly. If you went and grabbed the vision processing VI again, you have to make sure that you properly get the error wired into this chain, and that we create the image size. That was actually a variable, so you'd have to go grab that and make sure you're doing that correctly if you're putting that back. But it's safe to get rid of things like that. Network tables, teams generally shouldn't be getting rid of. This is used for the dashboard. This driver station start comm is critically important. And then the things inside this loop here are, they're user code getting called in each of the appropriate modes. So you want to make sure that those stay put where they are. We'll open up time tasks real quick just to show what the structure of this should look like. Pitfalls here. Everything in here should generally be in loops. As you can see in robot main, there's no loop around this. You know, in teleop, there was a loop around it. Teleop is getting called each time every 20 milliseconds. Periodic tasks, time tasks, is not. So any loops, you have to have yourself inside of here. So there's some examples, 10 millisecond, 100 millisecond loops. In this VI, you do want loops. If we put something like, and you wouldn't drive in here generally, but you can. But if we threw something in here, right, and we're taking our robot drive, and say we were driving it off joystick values, but I'll just create some constants. This is only going to run one time, which is often probably not what the team expects if they're putting this in here, because you'd probably put it in begin if you only wanted it to run once. There's no real reason to put it here in periodic tasks. So they should have a loop around it. I drew that bigger than I needed to, but we've now got a loop around it, and we're going to run that task at a 20 millisecond rate. So now we're setting our drivetrain, and we'd probably do it on joysticks, but we're setting our drivetrain every 20 milliseconds in periodic tasks. The reason teams may do something like this is generally if they want to control the same code from autonomous and teleop. So they write code for how a system works in here, and then they feed it set points from the autonomous or teleop VI depending on the robot mode, but it feeds into the same sort of state machine or something here in periodic tasks. That would generally be the reason you'd see a lot of code in here. Other than some basic, tasks that you want to run periodically. So that's a quick run through of debugging in LabVIEW and sort of the top couple pitfalls to look out for in the teleop and periodic tasks robot main VIs. I guess the last thing we'll cover real quick is we'll open the autonomous independent. We talked about one of the big autonomous pitfalls, which is not using this delay and feed and just using a regular delay. That's the biggest one in here. As you can see, the provided ones use this delay and feed, and they have things chained together. This one has a for loop. So these are used, you can see this array here that sets how many times the for loop gets covered, and the array is provided here of these two 1 second movements, turning one direction, then turning back the other direction. So you can see with the for loop, that keeps the things in line. With this other one, they're chained. So one of the big things in autonomous is teams may expect things to go in a sequence, but they don't wire them together. So let's say instead of chaining these together, we broke them free, and we had this guy sitting down here somewhere. So this is going to cause a big problem because we're setting the motor two different ways at the same time. Actually, with this delay here, we wouldn't be. So now we're trying to set it twice. We don't really know which of these is going to win, but one of them will. LabVIEW will just pick one of these to execute first and one to execute second based on allocating threads from the thread pool. And so I'll just wire this in here. So this would not behave the way the team expects. And that's a pitfall in autonomous. It happens even more often in teleop, where they have case statements and they're setting something. Let's hop back to teleop and show an example of what I'm talking about here. So if we make a case structure here and a case structure here, so we want something to happen. We want, if a button is true, so we've got our buttons here. If a button at 0 is true, we do something. And if a different button is true, we do something else. So what some teams will do is these two somethings happen to work on the same motor. So we'll open a motor real quick. And we'll set it in here and set it in here. So the open wouldn't usually be in here, but this shows a quick example of what I'm talking about. So some teams will say if button 0 is pressed, I want this motor to run forward. And if button 1 is pressed, I want it to run backward. So the problem we've created here is if both buttons are pressed, we don't know which way the motor will run. And if neither button is pressed, we don't know the motor will just keep the last value. So this is not the way we want to set this up, because especially what the teams tend to do is they don't want to keep the last value, they want to stop when it's false. So they put this in here as well, and they stop, and they do the same thing in the other one. So now when I press button 1 and let go of button 0, I get what I have on the screen here. This one's false, this one's true, and they're both trying to run at the same time and set the motor, and LabVIEW's just sort of picking a winner for them. So either the motor doesn't run in reverse at all, or it stutters, or something goofy like that. So you don't want to set up case structures like this. Instead, to do this same type of behavior, what I would do, there's a couple different approaches, but I would throw some of these guys in here, these selects. So we say if button 0, so if button 0 is true, we want the motor output to be 1. So we'll grab this guy, and if it's true, it'll be 1. Let's say if button 0 is false. So now we need to know what to do if button 0 is false, right? So we're going to grab another one of these guys. So if button 0 is false, we're going to do this one for button 1. So if button 0 is false, we want to check button 1. So that's what we just did here, basically. We're going to put a 0 here because we want to stop if neither button is pressed. All right, so what I've whipped up here real quick, we'll put our motor output outside the case, get rid of our case. All right, so let's check out what the behavior of this does. This may be more like what the team wants. So we go in here first, we check button 1, and if it's true, we're going to pass -1 up this wire. Then if button 0 is true, we're going to grab 1. If button 0 is false, we're going to grab what we grabbed here. So basically what this is going to do, if I press button 0, regardless of what button 1 is doing, we're going to go forward. So button 1 is my winner here. If I press both, button 1 will control and I'll go forward. Or button 0 will control and I'll go forward. Button 0 is sort of my primary. If button 0 isn't pressed, we're going to go down and check this other one. Obviously, it doesn't execute in this order. It actually executes in the opposite order, but this is a good way to think about it. If button 0 isn't pressed, we're going to go down and check this other one. If button 1 is pressed, we'll do what it wanted to do. We'll go backwards. If it's not pressed, so if neither button is pressed, then we'll stop. So that's a quick way to do these button fixed constant controlled motor values that isn't going to run into that issue with case statements. You can do similar things with nested case statements or things like that, but the key that you want to make sure of is that there's only one set for any given motor. Because if we have multiple that are all floating around here in parallel, whether they're in case statements or not, ultimately the behavior is going to be really erratic. LabVIEW is just going to sort of pick one, and maybe it'll pick the same one most of the time, maybe it won't. But you're not going to get, sooner or later, this is going to come back to bite you. So you want to make sure there's only one set for every motor. And whether it's nested case statements or these select statements here, these select nodes, you want to make sure you only have one set for every motor in a particular VI, autonomous or teleop. So that wraps up this video on LabVIEW debugging.